launch base for Ariane 6 is in its finalisation phase. On one side, the launcher assembly building, and then the launch pad itself, with the big mobile gantry. Here, Ariane 6's boosters and fairing with payloads will be fitted. Ariane 6 facilities are taking shape. Europe's future launches are becoming reality.
So first Ariane 6, the development goes full speed ahead, and now industry has started the production of the first 14 launchers of Ariane 6 in addition to the maiden flight. So 15 launchers in production today. On Vega-C side, all engines are tested, and we had the test of the Zefiro 40, which was the last engine test. So now we are really on the final path towards the maiden flight of Vega-C as well.
Vega-C is the new and enhanced version of Europe's lightweight launcher Vega. It will allow for an increased and versatile payload capacity from Kourou. In parallel, ESA is supporting the development of a structure to launch multiple satellites, called Small Spacecraft Mission Service. This dispenser allows more than a dozen small satellites to be launched under the fairing of Vega and then Vega-C, which will soon launch from Kourou for the first time.
We will have a proof of concept flight on Vega, allowing to launch light satellites, a big number of small satellites. And we are already now preparing the same for Vega-C and Ariane 6. So all our European launchers, which are in development today, will have the capacity to offer a launch of a number of small satellites, light satellites. It's a real market enhancement.
Another project for ESA is Spacerider. It is the continuation of the Intermediate Experimental Vehicle, IXV, the successful mission that flew in February 2015. Spacerider is an unmanned orbital vehicle that should provide Europe with its first operational reusable space transportation system. It will be able to return from space and will allow for experiments in microgravity, in-orbit validation of technologies, deployment of small satellites, and might even be used for Earth observation applications or servicing missions.
We have today the access to space component, which is covered through Ariane 6 and Vega-C. We are developing at ESA STS Space Transportation also propulsion elements, engines for transport in space, and with Spacerider we have an operational capability which will have to be decided in Sevilla end of the year for returning from space on Earth.
While the Ministerial Conference in Seville will decide on the further development of Spacerider, today, with its range of launch vehicles, Europe is already able to launch any type of satellite into any orbit. The new portfolio under development aims to further secure this approach on the commercial launcher market, and at the same time ensures Europe's independent access to space in the future. In the forests of Lamphaushausen near Stuttgart lies the German Aerospace Agency's Institute of Space Propulsion. Over the last 40 years, nearly all the liquid propulsion engines of every version of the Ariane launch vehicle have been tested here, and ESA's new Ariane 6 is no exception. With its maiden flight in sight, many of its components are being checked here. To accommodate this new vehicle, several of the test facilities have been modified.
So for the moment we have the P4-1, which is a high altitude test facility where we have made already the development and qualification testing of the Vega-C engine. And we have the P5, which is testing currently the main stage engine, the Vulcain 2.1 for the Ariane 6. And we are now in the process of accepting the new test facility for the upper stage, which is called the P5.2.
This P5.2 facility is new and has been specially built to test Ariane 6's upper stage. It looks like a launch pad, complete with different floors in a tower, similar to the ones at Europe's spaceport in French Guiana. Operations inside this facility are monitored from a central control room. After final preparations, a countdown marks the start of the test, just like an actual rocket launch. The Ariane 6 upper stage incorporates the Vinci reignitable rocket engine. This reignition is a key feature, adding versatility to Ariane 6 missions. While this engine has already been hot fire tested, it's essential to also understand the overall behavior of the whole upper stage before Ariane 6's maiden flight.
In the development of a launch system, you want to test the stages in the closest condition to the flight one. So we want to have a real stage test and not just engine test, which is performed in another test bench close by here.
At the Ariane 6 upper stage test stand, all aspects of the flight are simulated, such as the preparation of the stage and also the flight itself. It's important to know how the upper stage behaves when the Vinci engine is running. The upcoming launch of Ariane 6 generates a lot of activity here in Lamphaushausen, but also in factories and research centres all over Europe, and of course in Kourou, where a massive launch pad is being built. Of Ariane 6, the approach is new. Design and manufacturing are done almost in parallel. An important task for ESA and European industry.
The difficulty of Ariane 6 and the challenge of Ariane 6 is also given by the schedule, and we know that we had a little bit more than 5 years to build the old launch system and to qualify the old launch system, and this is a real interesting kind of challenge that we have, because we have to coordinate, synchronize many developments at the same time.
Despite this tight schedule, the many parallel builds and developments, ESA and industry accepted the challenge to develop this launch system in only 5 years. Today, Ariane 6 is scheduled for its maiden launch in 2020. From Kourou to Lamphaushausen, the development of Ariane 6 continues at full speed in order to offer a competitive launch vehicle for the commercial market, while at the same time securing Europe's independent access to space.
and welcome to space. And this month we have a unique chance to visit this place behind me, the Avio rocket factory just south of Rome, where engineers are producing the next generation of carbon fibre European launchers. It's rare to get the chance to film in one of these places, so let's get down there, meet the team and find out what's new.
This is one of the very few space rocket factories in Europe, the place where the lightweight Vega launcher was born and where the rockets of the future are being created.
This is the Vega rocket factory. The casings of the first, second and third stages of the launcher are made here. These casings constitute the load-bearing structure of the motors. Here in this building we start from the raw materials. The rubber and carbon fibre comes in and the rocket casings come out, ready to be loaded with propellant.
Most big space rocket bodies are made from metal, but Avio uses carbon fibre for the Vega, and it does so with a unique patented winding technique. The goal is to have maximum bang for your buck.
The key parameter in this design is its lightweight, because obviously a rocket needs a lot of power to get into orbit, but also has to be as light as possible.
5, 4, 3, 2, 1, top.
Just watch a launch and you can see what Vega can deliver. Solid propellant rockets like this can't be throttled back once ignited, but they offer enormous thrust right off the launch pad.
It's like extremely fast and quick rocket to lift off because it's very light. It's relatively light with respect to the thrust that it gets at liftoff. So it is really like a tremendous emotion and impression that you get.
Vega rockets may shoot off the launch pad, but building one is a slow and careful process. It takes a year to go from raw materials to launch. And the first step is to use a kind of giant tube-shaped mould called a mandrel.
To make a rocket motor in carbon fibre, you start with a piece of equipment like this. We call it a mandrel. It's made of many metal pieces assembled together, and on this rotating part of the machine, we wind the carbon fibre. During operation, a rocket motor reaches over 3,000 degrees centigrade. So to protect the structure from these high temperatures, we fabricate this thermal insulation, which is a very thin rubber, and that's the first thing applied to the mandrel. Then we start with bobbins like this. This is pre-impregnated carbon fibre with epoxy resin, which is an Avio patent. And with this material, about 5,000 kilometers worth of this filament, we wind the carbon fibre structure onto our mandrel.
Avio has just used that carbon fibre winding process to create the P120C, the largest rocket engine of its kind ever made. The P120C is important as it will be the first stage of a new, more powerful version of Vega called Vega-C. This, the first one made, just passed a static fire test at Europe's spaceport in French Guiana. The same engine will be used in the forthcoming Ariane 6 in a drive to head off competition from India, China and the US.
In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega-C and the Ariane 6, the P120C solid rocket motor, that enables the possibility to harmonize resources and to have the same motor serving the Vega-C as a first stage, as well as the Ariane 6 in both configurations as a strap-on boosters.
With the first Vega-C launch planned for 2019, there's another effort underway to upgrade the rocket's upper stage. This is the part of the rocket that actually flies through space and delivers the satellites into the orbits that customers have asked for. It's the only stage that uses liquid fuel, meaning it can be turned off and on again, unlike the solid propellant engines.
In particular,
on Vega-C, we developed the fourth stage so that it can carry satellites with a much larger mass compared with Vega now, and it's capable of restarting several times. This allows a lot of flexibility in the new launcher, which can launch satellites from the very small CubeSats, weighing just a few kilos, to those weighing 2,500 kilos, which is very big for our launcher.
500 kg, quindi estremamente grandi per il nostro lanciatore.
With the lightweight Vega, mid-sized Soyuz and heavyweight Ariane 5, ESA's range of launchers can now reach any orbit from French Guiana. And this youngest member of the family continues to make its engineers' hearts leap every time it flies off the launch pad.
See it.
The power that comes out from inside the engine, both in terms of the flames coming from the nozzle and the deafening noise surrounding the launcher and the engine, is really exceptional. And the first time, it's like your first love. You'll never forget it.
And now to the part of the show in which we take your questions about the universe and put them to the experts using the hashtag #AskSpace. And we're here inside the Avio rocket factory with Giorgio Tomino from ESA. Giorgio, we had a question from Veronica Remondini. She would like to know to what extent we're introducing this concept of reusability into rockets in Europe.
Yes, in fact, we are already working on reusability in Europe and in particular in ESA since several years. I go back to the successful mission performed by Vega on the fourth flight with the IXV re-entry technology demonstrator, where we have tested in flight all the critical re-entry technologies. And in addition, in the longer term perspective, when we talk about Vega-E and the investment we are doing to develop the LOX methane engine, which is intrinsically reusable, we could think as the longer term picture to bring down not only the re-entry module, but also the orbital service module, so the complete stages to be relaunched for the next flight.
Thanks very much for that insight. Fascinating stuff. Send us your questions about the universe using the #AskSpace hashtag and we'll try to answer them, and you can follow other space news on Euronews.com.
Italy had this, let's say, this will to develop a new launcher, and they started with several studies of small launcher, and then they came in '98 with this proposal to ESA.
Top. Allumage premier étage. Décollage.
The P120C solid rocket motor enables the possibility to harmonize resources and to have the same motor serving the Vega-C as a first stage as well as the Ariane 6 in both configuration as a strap-on boosters.
This is the Avio factory in Colleferro, Italy. This is where the carbon fibre casing for the first, second and third stages of Vega and also of the future Vega-C are developed. To build them, 5,000 kilometres of carbon fibre impregnated with epoxy resin is wound around a pre-made metal mandrel. This produces the very lightweight but sturdy casings for the first, second and third stages of the Vega launcher. These cases are later fitted with an engine and loaded with the solid propulsion. One of these solid propulsion engines is the P120C. It was recently successfully tested in Kourou. It is the largest and most powerful monolithic solid propulsion motor ever built. With Vega-C, ESA hopes to respond to launcher market demands.
So certainly in the launcher sector, the competition is growing worldwide. But we believe that the European answer, the ESA answer with Vega-C and Ariane 6 is the right answer. In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega-C and the Ariane 6, the P120C solid rocket motor, that enables the possibility to harmonize resources and to have the same motor serving the Vega-C as a first stage as well as the Ariane 6 in both configuration as a strap-on boosters. So this is a very good answer to tackle the competitiveness aspect.
Thus, with Vega-C, the C standing for consolidation, ESA is further developing Vega. It will add an increased performance to the flexibility of the current system without increasing the costs. Today, Vega can launch up to 1.5 tons on a 700-kilometre orbit. With Vega-C, this will be 2.3 tons. In order to increase the performances, two new solid propulsion engines have been developed. The P120C, but also the Zefiro 40 for the second stage. Further enhancements are made with Avom Plus, which is derived from the current Vega's Avom upper stage. It will be lighter and have a larger fairing for bigger payloads. These changes also have implications for the Vega launch pad in Kourou.
We've foreseen a lot of activities to modify the launch site from the Vega configuration to the Vega-C configuration. Vega-C is a heavy, larger and length launchers with respect to the Vega one. So for this reason we have to modify the hatches to the stages, increasing the diameters for what concerns the first stage.
Other changes include modified fluid services and the installation of a more powerful crane needed to lift the heavier second stage of Vega-C. During these modifications, the site has to remain operational for the scheduled Vega launches. In the end, the launch site will be compatible with both launchers. With Vega-C, ESA is also working on related products, such as the Spacerider, based on ESA Experimental Re-entry Vehicle IXV. It should allow for payloads to be sent into orbit and later returned to Earth.
In addition to this, we have other products like a specific adapter for launching into orbit small spacecraft, so enabling the possibility of universities and research centers to access space at limited cost, so coping with the payloads which go from 1 kilogram up to 500 kilograms. We also have early elements of definition for a platform called Venus, which could allow payloads to transfer from orbit to orbit.
With Vega-C, ESA aims to offer an improved, flexible and reliable launch system to the commercial and institutional market worldwide. With its ever-expanding family of launchers, ESA continues to secure independent access to space for Europe.